Okay, so after this what we are going to discuss is unsymmetrical bending. Unsymmetrical bending, first of all we will try to understand where is it coming from, and then what are the cross sections which we can use to which causes unsymmetrical bending. Unsymmetrical bending is caused by a movement in about particular axis. Now, if you remember when we were deriving our Euler-Bernoulli equation, we discussed different equilibrium conditions. We said that there are essentially two types of equilibrium condition. One is summation of all the forces must be equal to 0, and another one is summation of moment must be equal to 0. So having three axes, we can say that we have got 6 altogether equilibrium equations. In those equilibrium equations, there was one essential equation which required summation of moment about y must be equal to 0. Okay, so my y is in this direction. Summation of moment about y must be equal to 0. That is an important equation. Now, if you see, if I have a rectangular section, okay, and this rectangular section has got a cross section, we take a small element. Okay, so remember that in this course, mainly we will divide our whole component into small elements. Okay, and then we analyze that element. So we can say that this cross section is made up of infinite square areas. We take one random square area, which is this one. Okay, so this has got three forces or three stresses mainly. One is stress XX, okay, which is in the x direction. One is tau yx, which is the shear in the y direction, and one is tau xz, which is the shear in the z direction. Okay, so these are the three shear stresses. Now, stress summation of moment about y must be equal to 0, so we take a moment about y axis. Okay, so what is that? We can say that, assuming that this distance is z. Okay, so stress x times z times z, yeah, integral. Why? Because they are infinite. Must be equal to 0. Stress xx times z, and stress xx is the stress. So how would we find out our area? Stress is equal to so we have stress times dA. So this stress xx we multiply with dA, that must be equal to 0. Okay, now remember we derived stress xx is equal to Ey by rho. That is right from our first class. stress is equal to Ey by rho, and that gives us then later what either Bernoulli equation. Okay, stress is equal to My over I. So plugging that in this integral, so this is Ey by rho z dA must be equal to 0. Now the curvature is constant for a particular cross section. Okay, so for all this cross section, curvature is constant. Okay, in other words, what is the curvature? We had a very long discussion on this. We take 2 points. Okay, we draw tangent at those 2 points, and then we draw normal, and that normal, when it meets a point, okay, so that is, and keeping that as center, we draw a circle in such a way that it touches 2 points and all the points in the middle. So that is called our radius of curvature. So that radius of curvature is constant at a particular cross section. For this whole cross section, which is dA, okay? For this whole cross section, curvature is constant, and E is also constant. So therefore, E and rho, they can be brought out of the integral. Why did I discuss this, whether it was constant or not? The reason is whether there is any term which you can bring out of the integral. You can always bring a constant out. Okay? So I can't bring y out, I can't bring z out. Why? Because y and z, they both are varying in the cross section. So therefore, we can't bring y and z out of the integral. Okay? But the cross section is not dependent on modulus of elasticity. Why? Because material is constant. Okay, we assume that the material is constant, it's made up of homogeneous material, and the radius of curvature, that is constant for a particular cross section. Okay, so this E and rho can be brought out. So this implies that E by rho must be equal to 0. Now, E and rho, they can't be 0. Okay, it's impossible to have E0 or rho 0. Why? Because it will have some material, and rho, because it will have some deformation. We are assuming that the structure has deformed, it has deflected. So therefore, the radius of curvature is finite, and the modulus of elasticity is finite, it can't be 0. So the only candidate which can be 0 is this guy. Okay? And what is this? This is a type of moment of inertia. And what is this called? In moment of inertia, what happens? We take an area element and multiply that with the lever arm raised to the power 2. The first area is dA times the lever arm. The second area is dA times twice the lever, 2 power lever arm. And this is dA times y and z. Okay, so that is also a special type of moment of inertia. Okay, and what is this telling us? This is telling us that if you take dA, okay, you take dA, and there is y and Z corresponding to that dA. Okay, you take the moment with this, you take a small element, multiply that with the Y lever arm and the Z lever arm. Okay, take a moment and you multiply that with the Y lever arm and Z lever arm. So this will have, and you sum it up. If you sum it up, you should get 0. That's what it is saying. So in other words, this is actually telling us that you should always, that your moment is about the principal axis. Okay, this condition will only be satisfied if you apply the load along the principal axis. Okay, so that's what this is saying. This is saying that you should always apply load on principal axis, and this is actually product of two lever arms. So therefore this moment of inertia is called as product moment of inertia. Okay, this is called as product moment of inertia. Now let us check this. Let us check this on this rectangular section. Whether this is 0, if we take any axis. Okay, so one thing you should remember, and that is that you can have two axes in any direction. Okay, we have got these two axes. Okay, and they can be in any direction. Okay, you should always take that direction. You should apply the load in that direction where your product moment of inertia is 0. Okay, you should always apply load in that particular direction where your product moment of inertia is 0. In other words, your axes should be oriented in such a way that they make the product moment of inertia equal to 0. So if we check these axes, this arrangement like Z and Y, whether this makes product moment of inertia 0 or not. See, if you have an element over here having Y and Z, Z is negative, imagine this is positive. Okay, in this direction, this is positive in this direction, and this is positive in this direction. So you have Z negative and Y negative. Agreed? For this one. But at the same time, you can have an equal section where your Z is positive and Y is positive, and these both elements will add up to give you 0. No, they won't give you 0. They will both add up. Okay, so if you have element where Z is negative, Y is negative, okay, and over here you have element where Z is negative, Z is positive and Y is positive. So you can add them up. They won't give you 0. So in order to cancel them out, you need two more elements which will give you negative dA. Okay, dA is constant. So if I take this axis, so over here you will have Y negative and Z positive. So Y multiplied by Z is negative. And similarly, I take this one, Y negative, Y positive, Z negative. So if I add all those four elements which are having the magnitude of Y and Z, keeping the magnitude of Y and Z the same, I add all of them up, I will get 0. Okay, so I can change. So that means that this Y and Z axis, that is a principal axis. Okay, do you understand that? if I imagine I omit this part of the section and I get only like this, I've just removed this. I've removed this. Now what will happen? I will have a section over here. Agreed? I take these two axes. Axes are the same. So I've got y and z over here. I've got y and z over here. I've got y and z over here. But I don't have any y and z over here. So I add them up. I won't get 0. So that tells me that for this section, which is an angle section, this is not the principal axis. I have to rotate these axes in a particular direction that I get principal axis, and then I apply the load at that. So we'll discuss this in detail in the next class. Okay? Thank you.